Hi, and you are very welcome to this presentation in which we are going to explore the aspects of memory management, that is with regards to operating systems. So let's get into it as memory management. Before this introduction that is written here, I can first give a little highlights of it, because when I talk about memory management, I mean being able to allocate the required amount of memory to the resources that require it, or to the running processes, the running programs. So that's what memory management is all about. So to sum it up all, it's a major function of an operating system out of the many existing ones. And then this one is about controlling, then coordinating, and providing the required amount of computer memory, ensuring that programs can effectively utilize the available physical and then virtual memory resources. And then it involves many tasks. Major tasks like keeping tracks of which parts of memory are currently being used, and then by which processes. So you can the operating system keeps track of which part of memory is being used, that is by using something called IDs or process IDs, and then the amount of RAM being consumed, that is the primary memory that we are talking about in this case when we talk about memory management. And another aspect is allocation and then the allocation of memory space as needed. So the operating system knows that this program, it requires this amount of space for it to run, that is RAM, and then it does that effectively. And also it decides which processes and data to move in and into and then out of the memory, that is by using a phenomenon called swapping. So it swaps between the processes which are currently into the RAM or the primary memory in that case. So what could be the importance of memory management? So I highlight the importance of memory management here, and I begin by ensuring optimal performance and then stability. Of course, if the operating system allocates well its space to these running programs or processes, then there it should be optimal, or it can be reliable and then stable for for executing those programs. And then also for effective multitasking, for you to be able to run multiple programs at a go, you need to allocate them space. There is a way to allocate space which we shall see in the slides, but that is the work of the operating system that says since you have these many amounts, or this number of running programs, let me allocate this amount of space or memory to you. It also does security, and this is also an interesting importance, because there are hackers who use this method of attack. They overflow or overwhelm you with a lot of requests so as to fill the RAM, or so as to overload the memory, so that they make your PC not available to the intended users. So that is an attack that an operating system hopes you to solve by allocating a required amount of space to the running processes, so that the attackers are not successful in doing that. So that's the aspect of security. Then there is ensuring proper utilization of main memory. For instance, there is this case where an operating system cannot, let me say it like this way, programs running cannot utilize the whole main memory. If you have 8 GB, then you might not be using the whole of 8 GB. As you might be using it, but someone just using the PC for reading might not utilize the whole memory. So the operating system looks at that, and then it determines the amount of space to give you always, or to allocate to you, so that you ensure the effective utilization of that memory that you have. So another aspect is or importance is to enable computer systems to run programs that require more memory than the amount of free main memory available on the system. That is something, or that is a phenomenon called virtual memory allocation. It's in different operating systems, Windows, then Linux. Then it's also there in Android, because Android has it's an operating system. And that clean architecture also gives what they call something called memory fusion. That is by borrowing the amount of some amount of space from the hard drive or from the ROM to the RAM, so that it can be able to accommodate other programs that require more main memory than the amount of free memory available. Though it might have its limitations to some extent, it might not give you all the amount of memory you want, or the additional that you want, but that's how it works. It also enables sharing of spaces among processes. Of course, that is, it can allocate different amounts of space to the processes running, even if one process is running at a time, or there are many. So the operating system looks at that, and then it does what they call memory management with that aim. So in memory management, we come to this allocation, and we look at an important aspect of allocating memory, or before understanding other complex aspects of it, there is something called logical and then physical address. The way this is written, logical is something intangible, and then physical is something tangible. Then MMU, which is the memory management unit, it is the one that plays between the two. It switches, it can help you to move, it can help you to borrow from physical or from logical. So this is a middleman, but then there is a logical address space that encompasses the range of addresses that a CPU can generate. Then this perspective from which a program sees its memory. So if it has this 4 GB of RAM, so the memory might not entirely be occupied by the all of those processes that you're using. So it cannot utilize the whole of it at the moment. So logically, it allocates maybe this 4 billion or 4 billion something bytes to a 4 GB of RAM system. That is the logical space that is intangible, so we cannot touch that, and that aspect is explained in that way. So there is a physical address space which looks at the physical RAM. So there it is the actual physical location in which in the memory hardware where data is stored. And then MMU, that is a middleman between the two aspects. So those are terms that we can meet before when we are looking at memory management, and they are worth looking at for sure. Then another aspect is contiguous memory allocation, and that, by the way, this is the flow of memory management. My slides are entitled in a way that these are the aspects we need to look at when we are studying memory management. So this is an outline. When we are going through this, the title of the slide means a different aspect of memory management. So this contiguous memory allocation, it refers to allocating or assigning contiguous blocks or fixed fixed blocks or chunks to a single process that is loaded into the memory. So it is straightforward, efficient in terms of execution, and it leads to issues with fragmentation, which we are going to see down, where we have to separate maybe those blocks into many pieces, so that we can be able to allocate processes the amount of space accordingly. So it has two types. There is a fixed partitioning, where the memory is divided into a fixed number of partitions, and so for every partition only one process can be accommodated. So this is very fixed, and you cannot it is not reliable, though there is another did I include it? There is another contiguous memory allocation technique. I think it's here. It is called variable partitioning, and then this one is continuous in a way that if you have fixed number of blocks, let me try to allocate something like this. If you have maybe these 1, 2, 3 and 4 blocks, and this there are processes incoming. The moment you open another process, it comes to and it wants to enter a fixed size or a fixed chunk. When that happens in variable partitioning, it keeps on looping, or it goes in this manner, the way I put this figure to allocate it that way. So that's how variable partitioning can be. So it is continuous in a way that the more processes you enter, the more this chunk or block is divided so as to accommodate those number of processes. So it is not as static as that one of a fixed kind. So then we look at fragmentation. This one is when the memory cannot be allocated to processes because the size of the amount of the available memory is less than the amount of memory that the process requires. So this comes in when we have the memory that has been maybe raw and it cannot be allocated to these different processes, or it is fixed. So this comes in to solve the problem, to solve that problem. And then fragmentation has two types, or has two ways in which it handles its processes. It has internal fragmentation, whereby the part of memory is left unutilized because it will not be used by any other process. Then the block is assigned to a process in a way that it is larger than the required block or chunk of space. And to clarify more about that, I mean, here the operating system allocates a lot of size to a particular resource, more than, even though it's needed like this, it gives it in excess so that it can be able to decide on how to allocate different processes, those blocks. And then we have external fragmentation, which has its other defects, because external fragmentation has some disadvantages in that the total amount of free available memory is sufficient to reside a process but cannot be used because it is non-contiguous. So if it is not fixed and it cannot be utilized, or it cannot be used, that is when you are trying to that is when you are intending to use external fragmentation. You are trying to go the hard way to assign this amount of space to the memory or to the process, but then it cannot be done that way. So there external fragmentation can be curbed or it can be decreased by using compaction or shuffling data in memory to arrange all free memory blocks together, and then have one larger free memory block that is usable instead of the other one, which was not contiguous and it was not to be used. So compaction is a solution to that external fragmentation, and there it moves all of the processes towards the top or towards the bottom, so that it does what they call shuffling. Compaction is the same as shuffling, so it moves them on top or on the bottom so that they can decide how to fill that block or chunk. So we have disadvantages of this. It can be maybe interrupts, and also the page fault can occur. It also consumes CPU time. Then we see another aspect of memory management as paging, which has a lot to do with virtual memory. So it is the memory management technique in which secondary memory is divided into fixed sized blocks, and those blocks are called pages, and also the main memory is divided into fixed sized blocks called frames. Here we have the secondary memory, which could be the hard drive, and also we have another memory which could be maybe the RAM. So for this RAM, it uses its fixed sized blocks as frames, and then the secondary memory, it uses them as pages. So each process, you have a process divided into parts, where each fixed size of the page can be having maybe the fixed size of the frame. So that is how it can be. If it is frame 1, it is page 1, and it has the same amount of space, 2 kilobytes. So another aspect is about this one is under paging, protection and sharing, and then it allows for the protection and sharing of reminiscence or maybe resources or phenomenon between these methods. And as each procedure has its own web page table that maps its logical deal with area or with correspondence to its physical address space. So that is about protection and then sharing as regards to paging. And then we have the advantages of paging. One, it can decrease it decreases external fragmentation that we had like we had already seen, so it is easy to implement. The operating system automatically, by the way, does this, and it doesn't have a lot of time doing it. It adds to memory efficiency. Then it since the size of the frames is the same as that of pages, swapping becomes quite simple. The moving in and out of processes becomes quite go over. Then we have, it is useful for fast accessing the data. And then we have another aspect of paging, which is called virtual memory. Virtual memory is that memory that is intangible, and it is part of the secondary memory that the computer uses as a primary memory. So in implementation of paging, virtual memory is key, and its secondary memory can be addressed as though it could be maybe part of the main memory. You saw an aspect that I was talking about called memory fusion, whereby an amount of space is picked from the main or from the secondary storage to act as primary storage. So we also have page fault, then working set, and then the data page when we are talking about paging. So those are the concepts that can also fall in. So page fault occurs when a program references a virtual memory page that is not currently resident in physical memory, Then the working set is the current or the number of actively used pages in the physical RAM. Data page, a page in the computer's memory that has been modified or written to during the course of the program execution. That is a data page. And the tendency of the program's memory access pattern to repeatedly reference a specific set of memory location. That is a locality of reference. So I had not put that there, but a locality of reference is what is referred to this. Tendency of programs memory access patterns to repeatedly reference a specific set of memory locations within a short period. So I will share these slides in this video description, and though the upload can be intended for another thing, but thanks for following up along. These are the references to the resources that I used throughout this presentation. Thanks. Bye.